Dealloying damage mechanisms as a part of uniform or localized loss of thickness. Description of dealloying based on API 571, Number A. Dealloying is a selective corrosion mechanism in which one or more constituents of an alloy are preferentially attacked, leaving a lower density, dealloyed, often porous structure. Number B. Component failure may occur suddenly and unexpectedly because mechanical properties of the dealloyed material are significantly degraded. Dealloying, also known as selective leaching, is a form of corrosion that occurs when one or more components of an alloy are preferentially removed by a corrosive environment, leaving behind a porous, weakened structure primarily composed of the remaining metal. This process can significantly reduce the mechanical strength of the material and often leads to catastrophic failures in structural components and systems. Number 1 is about mechanism of dealloying. Electrochemical process. Dealloying is driven by electrochemical reactions, where the more noble, or less active, metal in the alloy remains while the more active metal is leached away. Corrosive environments. Common media that can facilitate dealloying include acids, alkalis, or other aggressive solutions that interact with the alloy. Initial attack. The process typically begins with localized corrosion or an environmental exposure that targets specific phases within the alloy, leading to the dissolution of the less noble metal. Number 2 is about common types of dealloying. Copper alloys. In copper-zinc alloys, brass, the zinc may be selectively leached away, resulting in a porous copper matrix that is much weaker and can lead to structural failure. Nickel alloys. In nickel-copper alloys, like Monel, the copper phase may be leached out in certain corrosive environments, particularly in seawater. Aluminum alloys. Dealloying can also affect aluminum alloys, especially under exposure to chlorides, leading to accelerated corrosion rates. Number 3 is about consequences of dealloying. Loss of mechanical properties. As the matrix becomes porous due to the removal of a key component, the remaining material can display significantly diminished strength, ductility, and overall structural integrity. Visual indicators. Dealloyed materials may show signs of pitting, rough surfaces, or changes in color and texture that indicate loss of material. Failure mechanisms. The degraded structure may lead to fractures, leaks, or catastrophic failures in components like pipes, tanks, or structural supports under stress. Number 4 is about factors contributing to dealloying. Alloy composition. The susceptibility of a material to dealloying largely depends on its composition and the specific environmental conditions. Environmental factors, pH level, temperature, and the presence of aggressive ions, e.g., chlorides, can greatly accelerate the dealloying process. Microstructure. The microstructural properties of the alloy, including grain size, phase distribution, and defects, can influence how rapidly and extensively dealloying occurs. In conclusion, dealloying is a significant corrosion phenomenon that affects the performance and safety of alloyed materials in corrosive environments. Understanding the mechanisms, recognizing the causes, and implementing preventive measures can help mitigate the risks associated with dealloying, ensuring the longevity and reliability of structural components. Dealloying affected materials based on API 571, primarily copper alloys, brass, bronze, tin, as well as alloy 400 and cast iron. Dealloying damage primarily affects metallic alloys, particularly those that contain more than one metal. Some of the most commonly affected materials include: Number 1 is copper alloys. Brass, copper-zinc alloys, brass, are highly susceptible to dealloying. When exposed to acidic or saline environments, zinc can be selectively leached, resulting in a porous copper structure. Bronze, copper-tin alloys, bronze, can also experience selective leaching, especially when exposed to certain corrosive solutions. Number 2 is nickel alloys. Monel, nickel-copper alloys, such as Monel, are at risk of dealloying, particularly in seawater, where copper can be leached out, compromising structural integrity. Inconel, some nickel-based superalloys may also be affected, depending on their exposure environments. Number 3 is aluminum alloys. Aluminum-copper alloys. Certain aluminum Cu alloys can undergo dealloying, particularly in chloride-containing environments, resulting in substantial loss of mechanical properties. Number 4 is aluminum alloys. Aluminum-copper alloys. Certain aluminum Cu alloys can undergo dealloying, particularly in chloride-containing environments, resulting in substantial loss of mechanical properties. Number 5 is cobalt alloys. Cobalt-chromium alloys. In some cobalt-based alloys, dealloying can occur when exposed to certain reactive environments, leading to changes in mechanical properties. Number 6 is silver and silver alloys. Silver-copper alloys. In dental applications, silver-containing alloys may undergo dealloying, primarily under acidic conditions where copper is removed, potentially leading to increased brittleness. Number 7 is tin-lead alloys. Found in solder applications, these alloys can experience dealloying in certain corrosive environments, particularly where the lead content is susceptible to leaching. In summary, dealloying can impact a range of metallic materials, particularly those that contain a more reactive, less noble metal combined with a more noble counterpart. The extent of damage varies based on the alloy's composition, environmental exposure, and the specific corrosion conditions present. Understanding the susceptibility of these materials helps in selecting appropriate alloys for various applications and environments to mitigate the risk of dealloying damage. Dealloying critical factors based on API 571. Number A. Factors which influence dealloying include the composition of the alloy and exposure conditions including temperature, degree of aeration, pH and exposure time. Number B. Dealloying occurs with several different alloys but is usually limited to very specific alloy environment combinations. Number C. Exact conditions under which dealloying occurs are often hard to define and damage may occur progressively over many years in service. Number D. Common examples of where dealloying has been found to occur are listed in Table 4.7. Table 4.7. Combinations of alloys and environment subject to dealloying. If alloy is brasses, greater than 15% Zn, that the extent of dezinification increases with increasing zinc content, and if environment is many waters, especially stagnant cons, then element removed is zinc or dezinsification. If alloy is gray cast iron, and if environment is soils, many waters, then element removed is iron or graphitic corrosion. If alloy is aluminum bronze, primarily with greater than 8% Al, and if environment is HF acid, acids with chloride ions, seawater, then element removed is aluminum or dealuminification. If alloy is silicon bronzes, and if environment is high temp steam and acidic species, then element removed is silicon or desiliconification. If alloy is tin bronzes, and if environment is hot brine or steam, then element removed is tin or destanification. If alloy is copper nickels, about 70 and 30, and if environment is high heat flux and low water velocity, then element removed is nickel or denickelification. If alloy is monel, and if environment is hydrofluoric and other acids, then element removed is nickel or denickelification. Dealloying damage occurs when one component of an alloy is selectively leached out, leading to the deterioration of the material's mechanical properties and structural integrity. Several critical factors influence the occurrence and severity of dealloying damage. Number 1 is alloy composition. Metallic phase, the relative reactivity of the metals in the alloy is crucial. Generally, the less noble metal, more reactive, is more susceptible to leaching. Secondary elements, the presence of other alloying elements can mitigate or exacerbate dealloying effects. Number 2 is environmental conditions. pH levels, acidic or alkaline conditions can accelerate the leaching process. Many dealloying processes occur faster in acidic environments. Temperature, higher temperatures can increase the rates of corrosion and dealloying. Chloride concentration, chlorides are particularly aggressive in causing dealloying of certain materials, like copper alloys in saline environments. Oxygen levels, oxygen can influence the electrochemical processes involved in dealloying, affecting its rate. Number 3 is electrochemical potential. Galvanic coupling, the presence of dissimilar metals in contact can create galvanic cells where the less noble metal is corroded preferentially. Potential differences. Variations in electrochemical potential in localized areas can cause uneven leaching, leading to localized dealloying. Number 4 is corrosive media. Type of corrosive agents. The presence of acids, bases, or salts can significantly affect the susceptibility of an alloy to dealloying. Presence of aggressive ions, in particular, species such as sulfides, chlorides, and others can lead to more pronounced dealloying effects. Number 5 is mechanical factors. Stress and strain. Mechanical stresses in materials can create localized anodic sites, enhancing dealloying in those regions. Surface condition. Surface roughness and the presence of microcracks can serve as initiation points for dealloying. Number 6 is time of exposure. Duration in aggressive environments. Longer exposure to corrosive environments typically increases the extent of dealloying damage. Number 7 is surface treatment and coatings. Protective coatings. The effectiveness and integrity of surface coatings can significantly reduce the risk of dealloying. Passivation. The formation of a protective oxide layer on some metals can prevent dealloying by inhibiting corrosion processes. Number 8 is microstructure. Grain size. Smaller grains may offer more numerous grain boundaries, which can be more susceptible to corrosion. Phase distribution. The presence of different phases in the alloy can contribute to localized corrosion and dealloying. In summary, understanding the critical factors that contribute to dealloying damage helps in selecting appropriate materials for specific applications, designing protective measures, and maintaining integrity under corrosive conditions. Awareness of these factors allows for better predictions of performance and longevity in service. Dealloying damage affected units or equipment based on API 571, Number A, underground cast iron piping when exposed to certain soils. Number B, in cooling water applications, heat exchanger tubing, brass, brass, is susceptible to dealloying in some brackish and seawater applications, but often the tube sheets suffer significant damage. Problems may also occur in some fresh or domestic water systems. Number C, boiler feedwater piping systems and afterboiler components may suffer dealloying, including bronze pumps, Monel strainers and brass pressure gauge fittings. Dealloying damage can affect a wide range of units and equipment across various industries, particularly those that involve the use of metallic alloys in corrosive environments. Here are some of the key units or equipment categories that are commonly affected. Number 1 is marine structures. Ship hulls and components. Copper alloys, like bronze, used in marine applications can dealloy due to seawater exposure. Offshore platforms. Structural components and piping made from susceptible alloys can undergo dealloying in saline environments. Number 2 is pipelines and storage tanks. Oil and gas pipelines. Copper and brass fittings can be particularly vulnerable in certain environments, leading to leaks and failures. Chemical storage tanks. Tanks made of certain alloys can experience dealloying when storing acidic or saline solutions. Number 3 is heat exchangers. Cooling towers and condensers. Components made of copper-based alloys can undergo dealloying, especially when exposed to aggressive water treatment chemicals. Number 4 is valves and fittings. Brass valves. These can be affected by dealloying, particularly in systems where water quality is poor or there are fluctuations in pH. Compressor fittings. Copper and bronze fittings might experience dealloying due to exposure to refrigerants or lubricants. Number 5 is electrical components. Connectors. Copper and brass connectors in electrical systems can undergo dealloying, leading to electrical failures and connections issues. Circuit boards. In some applications, solder, tin lead or other alloys, can experience dealloying under corrosive conditions. Number 6 is aerospace components. Aircraft structures. Components made from aluminum alloys, particularly those exposed to harsh environments, can suffer from dealloying. Engines and turbines. Certain nickel-based superalloys may experience localized dealloying under extreme conditions. Number 7 is medically implanted devices. Dental alloys. Some dental alloys can undergo dealloying, leading to loss of strength or increased brittleness over time. Orthopedic implants. Metal implants exposed to body fluids can experience dealloying, particularly if made from susceptible alloys. Number 8 is consumer products. Jewelry. Certain alloys used in jewelry, e.g., silver-copper alloys, may experience dealloying when exposed to moisture or acids in skin or environmental conditions. Monuments or decorative items. Brass or bronze statues and ornaments can dealloy over time, leading to aesthetic and structural degradation. In summary, dealloying damage can have significant implications for the safety, performance, and longevity of various units and equipment across many sectors. Being aware of the materials involved and the environments they are subjected to can help in making informed material selections and maintenance practices to mitigate the effects of dealloying. Regular inspections and the use of protective coatings can also be effective in preventing or minimizing damage. Appearance or morphology of dealloying damage based on API 571, Number A. There is often a significant color change or a deep etched, corroded, appearance as one element is removed from the alloy. However, depending on the alloy, the outward appearance of the affected material may not be noticeable upon visual inspection, even where the full wall thickness is degraded. Number B. Attack may be uniform through the cross-section, layer type, or it can be localized, plug type. See Figure 4-101, cross-section of a silicon brass alloy C87500 pump impeller from stagnant firewater service. Layer type dezincification depleted the zinc and left this porous red color of the copper. Mag. 50X. See Figure 4-102, a zone of denickellification in a Monell valve plug, at the port, due to oxygen contamination in hot hydrofluoric acid. Number C. In some cases, the original material is completely dealloyed yet the component exhibits virtually no dimensional or other visible changes. The appearance and morphology of dealloying damage can vary significantly based on several factors, including the specific alloy involved, the environmental conditions, and the nature of the dealloying process. However, there are some common features and characteristics that typically characterize dealloying damage. Number 1 is surface changes. Pitting. Dealloying often results in localized corrosion that manifests as small pits or cavities on the surface of the material. This is particularly common in copper alloys. Loss of gloss. The surface may lose its original shine and appear dull as the metal is leached away. Color changes. Depending on the alloy, dealloying can lead to color changes, e.g., copper alloys can turn greenish or bluish due to the formation of corrosion products like cuprous oxide. Number 2 is porosity. Formation of voids. As the more reactive component of an alloy is leached away, voids or pores may form. This porosity can be visible on the surface or revealed upon cross-section examination. Honeycomb structure. In some cases, particularly with copper alloys, the remaining structure may take on a honeycomb appearance due to the selective removal of one component. Number 3 is microstructural changes. Grain boundary attack. Dealloying often preferentially attacks grain boundaries, leading to an uneven surface morphology that can be observed under a microscope. Phase separation. The morphology may show distinct phases or grains that appear altered or corroded differentially, often leading to a layered appearance. Number 4 is corrosion products. Precipitate formation. The byproducts of the corrosion process may accumulate on the surface, resulting in crusts or films that can vary in color, greenish or bluish for copper alloys. Oxides and salts. Depending on the environment, various metal oxides or salts may form on the surface, contributing to discoloration and roughening. Number 5 is localized damage. Localized weakening. The overall integrity of the material may be compromised, leading to fractures or breaks that can be attributed to the loss of critical alloy components in localized areas. Deterioration of mechanical properties. The affected areas may show signs of reduced strength and ductility, resulting in cracks or failure under stress. Number 6 is surface roughness. Altered texture. Dealloyed regions may exhibit increased surface roughness due to the uneven removal of material. This can be quantitatively assessed using surface profilometry. Visual representations. Microscopic imaging. scanning electron microscopy, SEM, can show detailed features of dealloying damage, such as pitting, grain boundary attack, and the presence of corrosion products. Optical photography, photographs of the surface can reveal widespread surface damage, discoloration, and pitting. In conclusion, the appearance and morphology of dealloying damage are typically characterized by a combination of surface features, porosity, microstructural alterations, and corrosion products. Identifying these characteristics allows for better understanding and assessment of the extent of damage, which is crucial for evaluating the material's remaining life and determining the appropriate maintenance or replacement strategies. Regular monitoring and inspection can help in early detection of dealloying processes in various applications. Dealloying damage prevention and mitigation based on API 571, Number A. It is often difficult to predict whether conditions will be conducive to dealloying in a particular environment or service, so that one must be cognizant of the susceptibility of certain alloys, and the possible resulting consequences. Number B. Resistance to dealloying can sometimes be improved by the addition of certain alloying elements so that a similar alloy with a different composition may be resistant. For example, tin tends to inhibit dealloying of copper alloys. Admiralty brass is inhibited by the addition of a very small amount of phosphorus, antimony or arsenic, and dealuminification of aluminum bronze can be prevented by heat treatment to produce an alpha and beta microstructure. Number C. Continued degradation of a dealloyed component can only be prevented by altering the exposure conditions or replacing it with a resistant material. Number D. Depending on the alloy-environment combination, cathodic protection or barrier coatings may be effective. Preventing or mitigating dealloying damage involves taking proactive measures in material selection, environmental control, and maintenance practices. Here are several strategies to help minimize dealloying effects. Number 1 is material selection. Choose resistant alloys. Select alloys that are less susceptible to dealloying, such as those with lower copper content or alternative materials that resist corrosion in the given environment, e.g., stainless steel instead of brass. Use protective coatings. Employ coatings, such as epoxy, paint, or galvanization, to protect susceptible alloys from environmental exposure. Corrosion-resistant alloys. Consider using alloys specifically designed for corrosive environments, like nickel-copper alloys, Monel, or high-performance stainless steels. Number 2 is control environmental factors. Environmental monitoring. Regularly monitor and control environmental conditions, such as pH, temperature, and salinity, especially in marine or chemical processing environments. Water treatment. Implement water treatment processes to reduce corrosive agents, such as chlorides and sulfides, in systems where water is a factor. Drainage and ventilation. Design systems to prevent stagnant water accumulation and provide adequate ventilation to reduce moisture levels. Number 3 is maintenance practices. Regular inspections. Schedule routine inspections and maintenance on components made from susceptible alloys to catch early signs of dealloying or corrosion. Cleaning procedures. Establish routine cleaning protocols to remove deposits or contaminants that could accelerate dealloying. Cathodic protection. Utilize cathodic protection systems, such as sacrificial anodes or impressed current systems, to reduce the electrochemical potential for corrosion. Number 4 is design considerations. Avoid crevice and galvanic corrosion. Design systems to minimize crevices and contact between dissimilar metals that could promote galvanic corrosion. Minimize stress concentrators. Design components to reduce stress concentrations that can exacerbate the effects of corrosion and dealloying. Number 5 is use of inhibitors. Corrosion inhibitors. Consider using chemical inhibitors in water systems that can reduce the rate of corrosion and thus the likelihood of dealloying. Passivation treatments. For stainless steels and other alloys, use passivation treatments to enhance resistance to corrosion. Number 6 is education and training. Staff training. Educate personnel on the importance of material properties, corrosion processes, and proper maintenance practices to enhance awareness and outcomes. Number 7 is alternative materials. Use non-metallic materials. In certain applications, consider using composites or polymers that are resistant to corrosive environments and do not suffer from dealloying. In conclusion, by implementing a combination of these strategies tailored to specific environments and applications, the risk of dealloying damage can be significantly reduced. Effective prevention and mitigation require a multifaceted approach, including careful material selection, environmental control, rigorous maintenance, and ongoing education to ensure materials maintain their integrity over time. Regular monitoring and assessment will also help in identifying potential issues before they lead to significant failures. Dealloying damage inspection and monitoring method based on API 571, Number A. Many alloys change color in the affected area, however, scale removal may be required to determine the depth of attack. Number B. Dealloying in brasses is visually evident by a reddish, copper color instead of the yellow brass color. Number C. Graphitic corrosion turns. Number D. Cast iron charcoal gray and the material can be cut or gouged with a knife. Number E. Metallographic examination may be required to confirm the extent of damage. Number F. A significant reduction in hardness may accompany dealloying, although affected areas may be localized. Number G. Acoustic techniques, loss of metallic ring, and ultrasonic attenuation are applicable, but UT thickness measurements are not. Number H. Fitness for service, FFS, analysis of dealloyed components should consider that the dealloyed portion may be brittle and contribute little or no mechanical strength or load-bearing capability. Detecting dealloying damage requires a combination of visual inspections and advanced monitoring techniques to assess the condition of materials over time. Here are some common inspection and monitoring methods used to identify dealloying damage. Number 1 is visual inspection. Surface examination. Regularly visually inspect surfaces for signs of pitting, discoloration, or irregularities that may indicate dealloying. Look for signs of corrosion products like greenish or bluish stains on copper alloys. Macro evaluation. Conduct macro-level assessments to evaluate the overall integrity of structures and components, especially examining areas prone to environmental exposure or crevice formation. Number 2 is non-destructive testing or NDT techniques. Ultrasonic testing or UT, use ultrasonic waves to detect subsurface flaws, thickness reduction, and voids that may have formed due to dealloying. Eddy current testing or ECT, this electromagnetic technique is effective for detecting surface and near-surface defects in conductive materials and measuring thickness reductions. Magnetic particle testing or MPT, for ferromagnetic materials, this method can help identify surface and near-surface discontinuities, although it's less commonly used for non-ferromagnetic alloys. Dye penetrant testing, a dye penetrant inspection can reveal surface breaking defects like cracks and pits, which may suggest dealloying issues. Number 3 is electrochemical techniques. Electrochemical impedance spectroscopy or EIS. This technique can be used to evaluate the corrosion resistance of materials by analyzing their electrochemical behavior and assessing degradation over time. Potentiodynamic polarization. This method tests corrosion rates by measuring current response to potential changes, helping to identify susceptibility to localized corrosion, including dealloying. Corrosion potential measurements. Monitoring the open circuit potential of alloys can indicate the likelihood of dealloying under corrosive conditions. Number 4 is surface profilometry. 3D surface profiling, optical or mechanical profilometry can assess surface roughness and quantify the extent of pitting or other morphological changes indicative of dealloying. Microstructural analysis, scanning electron microscopy or SEM and transmission electron microscopy or TEM provide detailed images of surface and microstructural changes, allowing for identification of dealloying effects at a microscopic level. Number 5 is chemical analysis. X-ray diffraction or XRD. This technique can help identify corrosion products and alloy phases that may be formed due to dealloying, revealing changes in material composition. Energy dispersive X-ray spectroscopy or EDS, often used with SEM, EDS can provide elemental composition data from affected regions, allowing for the detection of leaching and the presence of corrosion products. Number 6 is monitoring systems. Corrosion monitoring sensors, install sensors that provide continuous monitoring of corrosion rates, such as electrical resistance probes or corrosion coupons, to detect changes over time. Visual monitoring systems, remote systems, such as cameras or drones, can provide regular visual inspections in hard-to-reach areas without disrupting operations. Structural health monitoring or SHM. Integrated monitoring systems. Advanced SHM systems incorporate multiple methods, such as strain gauges, accelerometers, to assess the structural integrity and detect any changes that might suggest dealloying or related failures. In conclusion, detecting dealloying damage effectively requires a combination of methods tailored to the specific materials and environments involved. Regular inspections, combined with advanced testing and monitoring techniques, enable early identification of dealloying problems. Implementing these methods as part of a comprehensive maintenance and inspection program is crucial for ensuring the long-term integrity and safety of structures and components susceptible to dealloying. By proactively identifying and addressing dealloying, organizations can prevent costly repairs and failures. Thank you.